Hello everyone, we are Group 42. Today we are introducing a neuro-symbolic approach for automated short answer grading. This is the structure of our presentation. Our work focuses on enhancing both the interpretability and accuracy of SEG system. Let's start with motivation. AG system improve efficiency and personalized learning. However, current models struggle with capturing thematic nonsense and lack transparency. While transformer-based models improve accuracy, their interpretability remains a challenge in practice. Our solution is a neuro-symbolic SEG framework that combines neural networks and symbolic reasoning to address the limitations. Here's how the system works. The first step is generating several labels for the raw dataset through weak supervision. Using multiple labeling functions such as lexical analysis, text similarity matrix, and linguistic rules, we assign initial labels to the dataset. These procedural labels are then aggregated and refined using a hidden Markov model to improve their reliability. The next step is to train a BERT-based large language model. The model learns to identify scoring points within student responses by analyzing the alignment between the answers and the rubrics. This stage is critical for extracting meaningful features and ensuring that the system captures both thematic and structural elements of the answers. The final step is the symbolic decision layer, which enhances the interpretability of the scoring process. Here, the scoring points identified by the BERT model are matched against predefined rules and based on the grading rubric.
We evaluated our framework on the SAF dataset, a bilingual corpus of German and English students' answers. Our system achieved an overall accuracy of 80% on the validation set, with a macro F1 score of 0.76. The macro position and recall were 0.8 and 0.73. When analyzing individual key elements, the model correctly predicted an average of 1.3 key elements per answer, while making only 0.42 incorrect predictions per answer. The SAF dataset provides a robust benchmark for our experiments. It contains bilingual student answers, reference answers, rubric, and scores. Importantly, it includes annotation guidelines, which we leveraged to manually construct symbolic rubrics. The justification queue model achieved high reliability with an accuracy of 0.8 and a micro F1 score of 0.8. To enhance training, we implemented strategies such as early stopping, linear learning rate decay, and small initial learning rate to prevent overfitting. The model demonstrated robust classification across diverse samples, although validation loss or silicates suggest minor generalization issue. We tested two symbolic methods. The decision tree method performed well. In contrast, the final summation method showed significant recall deficits. This highlights the limitation of simple aggregation method in capturing nonsense grading criteria. We also analyzed the RMSE trend across training epochs. The RMSE dropped sharply during the first epoch and stabilized by the second epoch, demonstrating rapid convergence. This consistency highlights the symbolic decision tree's effectiveness in capturing the nonsense of short answer grading tasks.
Here is an example of our workflow. We use student answer and scoring rubric as the input. And we use justification queue detect model, which is MDBERT version 3, to extract the key element from the student answer. And we use BERT score to compare the key element with the scoring rubric to get our scoring vector. We use symbolic model like a decision tree or the summation to get the final decision, which means get the final score. And for the limitation, we lack of gold-labeled justification queues, so it may cause concern about the quality of the silver label data. And the second is symbolic reasoning challenges. And the third part is the performance optimization. To address these problems, first is improvement of symbolic reasoning, and the second is efficiency optimization. And the third part is adaptation to other educational NLP tasks. The last one is feedback, and we plan to add some feedback to our model to make the explainability more powerful. And this is the references. And thank you for watching our presentation.